Okay, so this is lesson 1 of your gases and gas laws. We're going to start with theory. This is called the kinetic theory. Some people like to call it kinetic molecular theory of gases. So you basically need to memorize most of this. Just in particular, you just need to memorize it. So gases consist of particles in constant random motion. Okay, it says they continue in straight lines until they collide with something, usually each other or the walls of their container. Okay, particles are point masses. They're small hard spheres with no volume. Okay, so they actually do have volume, but it's negligible according to kinetic molecular theory. Okay, so it says the particles are so small compared to the space between them that we do not consider their size. Okay, we do not consider their size in ideal gases. No molecular forces are at work, so no intermolecular forces. You remember those IMFs? The hydrogen bonding and dipole-dipole interactions and dispersion forces. There's none of that going on in an ideal gas. Okay, so that means there's no attraction or repulsion between the particles. Okay, gas pressure is due to the molecules colliding with the walls of the container. Okay, so that's what gas pressure results. So right now there's like particles that are hitting you fairly hard, and that's the atmospheric pressure around you, is those particles hitting you. So gas pressure is due to molecules colliding with the walls of the container. All of these collisions are perfectly elastic, okay? Meaning there's no change in energy of either of the particles or the walls upon the collisions. And so no energy is lost or gained from the collisions, okay? So you know how like if you're bouncing a ball and like you let go, it kind of bounces a little and then dampens to where it just stops. There's none of that. That would be a loss of energy due to something else that maybe was not elastic. So we're saying that this is elastic. So if you like or bouncing a tennis ball, if you just let the tennis ball bounce, it would bounce and bounce and bounce with the same energy forever. That's what we're saying gas particles are like, elastic. Okay? Okay, and these last 3 parts, these are not necessarily part of the kinetic molecular theory. But they're just good things to know. Okay? So an increase in temperature increases the speed in which the gas particles move, and all gases at a given temperature have the same average kinetic energy, because kinetic energy is a measure of temperature. They kind of go hand in hand. And lighter gas particles move faster than heavier ones. Okay? So I don't know why there's these 3 postulates. This is basically saying the exact same thing that it's saying up here, but in less detail. So, all right, so what is gas pressure? Again, gas pressure results from the force exerted per unit surface area of an object. So the particles are hitting an object, and anyway, but gas pressure is a measure of how much force is exerted when those collisions are made. Oops, I should probably scroll down. There you go. Okay. All right. So gas pressure is a result of simultaneous collisions of billions of rapidly moving particles within an object. So gas pressure is the result of simultaneous collisions, gobs and gobs of them. An empty space with no particles is called a vacuum. We say that outer space is a vacuum. It's not that it doesn't have any particles in it, it's that the particles are so far apart that they do not interact with each other very much. So they might pass by each other going really fast, but they do not have time to interact. So we would say that it's a vacuum. Okay, and then atmospheric pressure results from the collisions of atoms and molecules in air with other objects, like you. Okay? All right, so you need to know your conversions. So in your reference material, there was a sheet of important gas constants, okay? And so those gas constants are on here. So you need to, I would print this out and I would just have this all the time. I printed mine out so I have the gas particle stuff on one side, and on the other side I put my periodic table so I could do some math with it, because they're going to have to do stoichiometry again. So, but this stuff, this is cool because it has standard temperature for gases. It tells me a conversion to get to the unit that I want for all my calculations. And look at that pressure. It has standard pressure in all of these different units. Okay? The main ones we're going to use are the kilopascals, the millimeters of mercury, torr, and atmospheres. So those are the main ones we're going to use. Nobody uses inches of mercury, nobody uses PSI, and I think the weatherman might use millibars or bars in America, but most of the time nobody really uses that either. So if you're a meteorologist, you kind of have to know all of these quite well and how to convert between them, but you're not, you're just a chem student. So and then there's volume relationships in case you need that for something. And then you have these gas constants in case you need that for something. And we'll get to that in lesson 2. Okay, so, but mainly what I wanted to point out was here's the pressure conversions. So I want you to be able to convert between different units of those. So I'm going to give you an example problem. Okay, so let's say I had 110.2 kilopascals, and I want to know how many torr is that and how many atmospheres is that. Let's call this A and we'll call this B. Okay, so for part A, what I would do is I would do dimensional analysis. So I do 110.2 kPa, and I would use my gas constant sheet, and it shows me that for every 101.325 kPa, I have 760 torr. Okay, so then my kPa's would cancel and I'm left with torr. So how many sig figs are in 110.2? Okay, so that would be 4 sig figs. So my answer must also be 4 sig figs. So I'm going to stick this in my calculator. Okay, so I get 110.2 times 760. Okay, so then that, oh wait, and then divided by 101.325. There we go. All right, so then I'd have to round that to 4 sig figs. That'd be 826.6. Okay. All right. And this thing over here, this little picture, this is a barometer. And this is showing you how we get millimeters of mercury. We have a tube with mercury in it. And at sea level, the standard pressure for gases at sea level is 760 millimeters of mercury. So we're saying in this tube, we have 760 millimeters of it filled with mercury. Well, when we go to Mount Everest, okay, where there's just it's at a very high elevation, the pressure is lower, so there's less collisions with the particles. Okay, so since there's less collisions, there's less mercury in the tube, so we go down to 253 millimeters of mercury when we go up in elevation. Interesting, right? Okay, so this is just a barometer. We use barometers to measure atmospheric pressure. Oh well, that's down at the bottom of the page. May as well highlight that while we're talking about it. So that's one type of thing that we use to measure pressure. That's what we use to measure atmospheric pressure. In a closed system, you'd use a different device called a manometer. Device to measure pressure in a closed system. Okay, so think of that as like a manometer would be a device like so like in Texas we have to do emissions tests on our cars to make sure that they align with EPA guidelines for what's coming out of the engine or the exhaust really. They use a manometer to measure the pressure of the gas, and then they can figure out what type of gas it is based on that. So manometer, closed system. barometer, open system. That's why it's atmospheric pressure for barometer. All right, let's do part B real quick before we get too off track. All right, so I want to go to atmospheres now. So I'm going to start with what I was given before, 110.2 kPa. And for every 101.325 kPa, that's equivalent to 1 atmosphere of pressure. So then kPa's cancel and I'm left with atmospheres. So then it would just be 110.2 divided by 101.325. And that gets me that. I need that in 4 sig figs. So it'd be 1.088 atmospheres. Okay. All right. So moving on. Okay. So we kind of talked about temperature in the KMT in the beginning. So average kinetic energy, right? Okay. So this is basically what we use to measure temperature. So basically, if you took like all the particles in a gas and you added them up and you measured how fast they were moving and you added that up, like, and took the average of how fast the particles are moving with regards to how many particles there were, you would have the average kinetic energy of the substance. So that would be the Kelvin temperature is directly proportional to the average kinetic energy of the particles of substance. That's basically what temperature is. That's the whole point of temperature. You have on your gas constant sheet, you have that let me scroll down here. The Kelvin temperature equals degrees Celsius plus 273.15. Well, also, if you wanted Celsius, degrees Celsius, you would do the Kelvin temperature minus 273.15. Okay, that's it. So let's do an absolute zero is 0 kelvins. So that is the point at which, and you need to know absolute zero. This is the temperature at which the motion of particles theoretically ceases. So they stop moving. So if they stop moving, they have no kinetic energy. Okay? We've never achieved this in a laboratory just yet. We just haven't. We've tried, and there are people on Earth trying, and you can go and find that somewhere in literature and read about it all you want. But for right now, no one has ever actually achieved that in a laboratory. And there's all kinds of theories about what would happen at absolute zero. So you can also go and read about that. You are not responsible for it for your test. Okay? What you would be responsible for is if I asked you some temperature conversions. So let's say I had 25.0 degrees Celsius and I want to know what is that in kelvins. Okay? Well, I would do 25.0 plus 273.15, right? And so stick that in my calculator. Okay. 25.0 plus 273.15. Okay. And I get 298.15 kelvins. So with sig figs though, since it's addition, you go by the least number of sig figs of any of your factors. Since 273.15 is part of the formula, it's considered a constant. We can't use it for sig figs. But 25.0 is the given. So this is one place past. So our answer would be 298.2 kelvins. Okay. For computation purposes, don't round anything until the very end. Okay. So if you were then going to use this number in something, I wouldn't round it to 298.2. I would round to 298.15, and I would stick that in my formula for computation purposes. Okay, so let's say I wanted, let's say I had 822 kelvins, and I want to know how much is that in degrees Celsius. Okay, so then I would do 822 minus 273.15. Now notice this has no places past the decimal. So our answer should have no places past the decimal. Okay, so we stick that in our calculator, and so that would be 549 degrees Celsius. Now, if I were using it for computation purposes, I would use 548.85. I would not round it Do not round anything until the end when you're using these numbers for computation purposes, and you will in lesson 2. Okay, so properties of gases. Okay, so we would assume that gases are very compressible. Okay, why? Well, compressibility is a measure of how much the volume of matter decreases under pressure. Okay, so it says when a person collides with an inflated airbag, the compression of the gas absorbs the energy of the impact, so they don't hit their head and hurt themselves. So compressibility, okay, so it says gases are easily compressed because of the space between the particles in a gas. So gas particles are spread very far apart, and then they collide with each other in the walls of the container, and that's what results in pressure. However, the compressibility of a gas is based on the fact that the particles are far enough apart that you can push them and squish them together a little bit. The distance between the particles in a gas is much greater than the distance between the particles in a liquid or a solid. If you compress them close enough, though, they will become a liquid. Okay, so under pressure, the gas particles are forced closer together. Eventually, if you press them under enough pressure, they will become a liquid. Okay, so that would be not ideal. We want to keep them a gas for purposes of what we're doing. So factors that affect gas pressure. So obviously gas pressure is going to be measured most of the time in either kilopascals or atmospheres or torr or millimeters of mercury. Okay, those are the main units we like to use for pressure. Any of those are fair game on anything with computation in your lessons. Volume always needs to be measured in liters. Temperature always must be measured in kelvins, and the number of moles can also affect the pressure of the gas, because if you have more particles, you'll have more collisions. Less particles, less collisions. So less collisions, less pressure. Okay, so it says you can use kinetic molecular theory to predict and explain how gases will respond to change in conditions. Okay, this is really important. This is important cause and effect. Of the kinetic molecular theory. So, if you inflate an air raft, for example, okay, the pressure inside the raft will increase because you're adding more particles inside of the raft. The collisions of particles with the inside of the walls of the raft result in pressure that is exerted by the enclosed gas. Increasing the number of particles increases the number of collisions, which is why the gas pressure increases. If the gas pressure increases until it exceeds the strength of the enclosed rigid container, the container will burst. Okay? All of that is important. That is the cause and effect. Like, this is why we use this, and this is a real life example that explains why kinetic molecular theory does what it does. Okay, one last thing, and then we will be finished with lesson 1. When we talk about forces of attraction, okay, we're talking about intermolecular forces. Intermolecular forces are, remember those things? The dispersion forces, dipole-dipole, hydrogen bonding, those are IMFs. Okay, those are your IMFs. It's important to note, for ideal gases, we consider them to have no intermolecular forces of attraction or repulsion. The gases are not repulsed by each other. They are not attracted to each other. They just whiz past each other in their particle form. And that's the end of lesson 1.